Okay, in this video, what we're going to do is talk about curves.
Curves.
Wow, this is going to be a technical lesson. And I got to tell you guys something right off the bat, and that is, in this particular video, I'm going to become more of a student than anything else. I'm going to be one of you guys out there, because I didn't major in math. I'm not a math kind of guy. And to be honest with you, I haven't used curves much outside of the world of modeling and perhaps path animation, and that's pretty much it.
Right.
I mean,
so animation curves.
Yeah, I've used, I've done spline modeling in the past, so I've used splines. I've used NURBS as well. I've done a lot of NURBS modeling. But that's pretty much it. So let's start out with this. First of all, why would I want to learn some of the math behind curves and the different kind of curves that are available to me?
Well, one of the reasons is, what if you want to go into your own applications and create curve management? Let's say you want to create your own 3D application.
Okay.
You want to have animation curves. Well, you need to know how exactly animation curves work internally to be able to calculate. Let's say you want to get a point along that curve.
Right.
You need to be able to, draw that on the screen. You may want users to sample that data.
Right.
There are just infinite amounts of reasons why you would have to know exactly how to do.
So the bottom line is just, in order to even create a curve within your application, you've got to understand it.
You have to understand what's going on.
That does make sense.
And not only that, I mean, from a programmer standpoint, you want to know how curves work.
Right.
But also, if you're doing any kind of scientific things in school,
curves become very handy.
Curves become extremely handy. You do in speech processing, image processing, just pretty much any area of science. When you start delving into it, you're going to hit curves at one point or another.
Okay.
And another thing is, there's not just one or two kinds of curves. I mean, you mentioned NURBS, splines. There are Bezier curves, there are Hermite curves, there are just a multitude of different kinds of curves.
Wow.
And this one, we're not going to obviously cover all of them, but we are going to touch on a few of the major ones and discuss how the math works behind the scenes.
Okay, and in the next video, we're actually going to create a little application that allows curve generation?
Yep, that's right.
Awesome.
And we're actually going to be utilizing some of the OpenGL utilities that make it simpler for us.
Okay, good deal.
So let me go ahead and go to the next slide here. This is a little bit of a hierarchy of how some of the curves or splines actually work. And a lot of people that I know don't like to split it up into this hierarchical form simply because it can become confusing. But at the same time, this is a really good way to see how the different curves are related to each other. So if you look on the very top here, we have our spline. And this is the most generic kind of curve that you can have. Okay. Which basically just says some sort of function that defines a smoothly interpolated line. It's a smooth line. And aside from that, on the left, we have our Hermite curve, and this is a type of curve that has tangents and points, and we'll look at these in more detail, just to kind of give you an overview of how these curves work. Okay. And on the right side here, a different
the good old B-spline
branch, yes, B-spline or basis spline. This is a very generic form of what a lot of people know as Bezier curves and NURBS curves.
Gotcha.
The B-spline basically says basis spline, which means defining a type of function that defines the curve. So basis functions help define the spline. And whether you're using NURBS or Bezier curves, that basis function or functions will change. So with Bezier curves, you have Bernstein polynomials that define how the curve works, how the curve is actually interpolating over its course from 0 to 1. A NURBS curve, on the other hand, uses a different set, and it has special properties that we'll talk about as well. And below the Bezier curve, we have a rational Bezier curve, which is an offset, a kind of variation of the Bezier curve, which allows each of the control points, which is the points that you use to define a curve, to have different weights. And you'll see how all this, I know this is probably really, really confusing at first.
Actually, as you're talking, I'm starting to think here. I'm like, hey, another use for them. I guess knowing this stuff would be really good if you were creating your own animation package and calculating what your animation curves would be like through your different keyframes.
Yes, exactly. You have to know that kind of thing.
Oh, so now I'm starting to see where curves is actually pretty important.
Oh, yeah. So let's go ahead and go to the next slide here and just look at Hermite curves. Okay. A very simple example here. I simply have 2 points, actually just a slight typo right there. This is P0 and P1. Okay. And then we have a T0 and T1, which is basically a point that starts out, the starting point, and a tangent for that point, and then the ending point and a tangent for that. And how you change these tangents will define how this curve is actually going to move. Okay. Which is very, very handy and actually used a lot in animation packages, allowing you to modify a tangent, which will modify the rest of the shape of the curve. And one thing to really note about curves is basically how they vary between each other is how the control points, which is these P0, T0, etc., are utilized. In this case, the control points are utilized as tangents and points, and Bezier, they're used to define a convex hull, which we'll see in a second, and so on. So that's kind of where the curves will differentiate. With Hermite curves, you can tie these together. I mean, you don't just have to have one small segment like we have here.
Right, so we can add another point in, tying yet another segment of the curve together, making a longer curve.
That's right. And if you want these curves to be smoothly interpolated together so that it has continuity, what you would do is simply attach another curve. Let's say we have a curve that comes into here, like so. We would have the end point connect to the beginning point of this one, and their tangents would have to be equal. They would have to go in equal opposite directions.
Unified at all times.
Right. Otherwise, you wouldn't get a smooth curve.
Right.
So that's Hermite curves, and that's not the kind of curve we'll be implementing in our own application. Typically, we'll be using Bezier curves or NURBS curves.
And you say we see these in animation packages, Hermite curves?
Yes, we do.
An example of where this would be used?
Well, to help modify it, like say in Maya, for example, in some of the curves you have tangent handles.
Right.
And that's exactly how this would be.
with Hermite curves that we're getting that. Okay.
So if we switch over into Bezier curves, now this is where a little bit more math comes into play. As you can see here, we have P0, P1, P2, and P3. This defines our control points for our particular curve. But this is utilized as a convex hull. These points basically define a convex hull. So if we connect these points from P0 to P1 to P2 to P3, it basically defines a very sharp version of our curve, right? And a way to visualize this, if you wrap a rubber band around all of these points here, this curve is always going to be inside of that particular curve. And what's cool about Bezier curves is you aren't just limited to 3 points. You can have 7, 8, 9, 10 control points. And by modifying those, you'll be able to change the shape of your curve. But because of the way Bezier curves work, modifying those points, especially if you have a lot of points, you don't get a lot of change, which makes it so that, you have a lot of local control.
Right.
The curve doesn't go absolutely crazy when you change one control point. If it was a pure interpolation curve, what you would get is this curve would always go through every single point, and it would try to maintain continuity for that.
Right.
Which means when you change, say, P1 to pull it all the way down here, the entire curve would change so that the curve goes through every single one of those points.
Well, we've got an application right now that's called Design Mentor by MTU. Or some students over there at MTU, that is a freeware application that will help us visualize these curves.
Right.
Is now a good time we can pull that up?
Yeah, sure. Let's go ahead and bring this over here. Let me just bring up the curve one as well. Got two little windows here. So a very simple application that allows us to visualize Bezier curves, splines, NURBS curves, etc. Let me go ahead and create a Bezier curve, because that's what we're talking about right now.
Exactly.
Let me just go ahead and drop 2 points in. 3 points. So what you can see here is we have a 2-degree curve that defines a complete curve. So if I go ahead and start moving this around, you'll notice that it's not going absolutely crazy when I'm changing this. It's not trying to reach this particular control point. And if I add more into here, let me go ahead and go back to create. Let me add a whole bunch of points here. Oh, well, it only goes up to 7 in this particular one. So let me go ahead and delete these last two here.
So it's just a 7-degree curve we have?
Yep. Let me go ahead and switch the move on. Check this out. When I'm changing this a whole dramatic amount, notice the curve doesn't change too dramatically.
A very localized type of control.
That's right. And of course, if you want even more control, what people will do is stream these together. So you have multiple Bezier curves tied together, and then you can have basically a patch modeling approach if you're used to certain animation or modeling packages, which will allow you to tie these curves together to create patches, if you will.
Cool.
And then you get more control that way. So this is basically the Bezier curve. So if I switch back over into here, what is the formula used to generate this? Well, basically we have C of t equals the summation from I equals 0 to n being the degree of the curve, multiplying the p sub I, which is the point, so the location of a particular point, x, y, or x, y, and z, multiplied by the Bernstein polynomial, which I mentioned before, I, n of t. And again, t goes from 0 at point 0 to 1 at point 3.
Now, the degree of the curve is always the number of points plus 1?
Right, it is.
Okay.
So if I come over...
Well, actually, it's just... Never mind.
come back over into here. Let me go ahead and remove some of these just to make it a little bit easier to visualize here. Not so many points to work with.
Yeah.
If I move this slider over on the right here, notice this little round circle here. So just keep an eye on that.
I just want to throw a correction in real quick. So it's actually the number of points minus 1.
Right, number of points minus 1.
Yeah.
Oh, I'm sorry. You said
I said plus 1.
Oh, okay, sorry.
And you said yeah, and then my brain started thinking, wait a minute, no, I said that backwards. But he said okay, so I'm not the curve man. But it's number of points minus 1.
Right.
That first one's always 0. It's our anchor point.
So notice we have 1, 2, 3 points, and the degree is 2, so 3 minus 1 is 2.
Yeah.
Right. So notice here, we have this slider here, and it's starting at 0. As we move it, watch as this circle goes all the way over to the end point. So it's going between 0 and 1
this is
at
kind
the
of
end.
the key thing here. Obviously, to be able to draw out that curve, we need to be able to sample any point along it.
That's right, so that we can draw little line segments to actually draw it.
Precisely.
So how do we actually calculate this? Well, I said we have the Bernstein polynomials, and I have this crazy function here. So what is the Bernstein polynomials? Well, let me go ahead and switch over to here. So the Bernstein polynomials, like as I said, are what allows us to calculate this Bezier curve. And this equals the binomial coefficient multiplied by t to the I power multiplied by 1 minus t to the power of n minus 1.
Okay.
So basically,
n minus 1 or n minus I?
N minus I, excuse me. And the binomial coefficient, for those unaware, is nk. This is equal to n factorial over n minus k factorial times k factorial.
Okay.
And if this is totally confusing to you, just accept it as a fact and just work with it.
Exactly. Well, the bottom line is this. We could have several VTMs dedicated on just this alone.
Yes.
You can simply
easily
put in the Bernstein polynomials and go out and do a little bit of research on the web.
Definitely. There's a lot of interesting things and uses for the Bernstein polynomials. A lot of interesting uses. Combinatorics is just one of them. So anyways, we have our n, or again, n is the degree of the curve, and t is a number from 0 to 1. So let me just do let me switch over to Photoshop real quick here and give you a quick example on how we could possibly utilize this. What options do we have to do this? So let's say we have this particular curve here, and let me just move it down to, say, right there. Let me go ahead and create this curve inside of Photoshop just using math and start defining exactly how this would work.
Okay.
So let me just switch over here. Let's say this is negative 60 and 22 for P0. If I switch over into here, so let me say P0 equals, do you remember what it was?
Negative 60?
Negative 60. And P1 is, I'm sorry. Let me just undo that. Negative 60 and 22, was it?
So I think it was 22.
22, yeah. So 22 and P1. Just bear with me here. Lots of writing out stuff. So if I come over to P1, this is negative 9.5 and 72. I'm just kind of rounding here to make the numbers easier. And then for P2, what I have is, come over to here, 27 and negative 2. Now, if you remember the formula we have for the curve, if I just write it up here, we have the summation from I equals 0 to n, which is the degree of the curve, taking p sub I, so we're going to loop through every single one of these points, multiplied by the Bernstein polynomial at I, comma, n at t. And we're just going to sample, if I come over to here, I'm going to sample at 0.3. Let me just move this up to 0.3. Something easy to calculate. So we're going to say t is equal to 0.3. Okay. And we're going to just calculate this once.
And t just runs from 0 to 1.
Exactly.
Okay.
So if I filled it in here, let me just do this. So I have I equals 0 to n of p sub I times b times I, comma, n of 0.3.
Okay.
And if I expand this just a little bit more, what you would get is negative 60, expanding the summation out here, times 22 of b sub 0. And if at any point this doesn't make sense, please let me know. So 0, comma 2, because the degree of the curve is 2.
That's right.
At 0.3, added to 0.1, so negative 9.5, 72, times the Bernstein polynomial at 1, comma 2, at 0.3.
Right. Plus,
just move this over here. And then this is going to be 27, comma negative 2,
right,
times Bernstein at 2, comma 2, at 0.3.
Okay.
Now
Cool.
we need to expand this entire thing out based on the Bernstein polynomials. And if I just switch over into PowerPoint real quick here, you'll notice I put some of the iterations for the Bernstein polynomials here. So we have at 0, comma 2, 1 minus t squared, 1, comma 2, 2 times 1 minus t times t, and 2 is t squared.
Okay.
So if I just come back over into Photoshop here, just kind of filling this in. So you have negative 60, comma 22. And then for the first one, for B0, comma 2, we have 1 minus 0.3 squared added to negative 9.5, comma 72 times 2 times 1 minus
0.3
times 0.3
0.3.
plus.
Joel, you're making this too easy now.
Isn't it too simple?
Yeah, actually, it's now becoming very clear.
Awesome. So we have negative 2, and then multiplied by 0.3 squared. Let me just put this in parentheses to make it easier. Now, at this point, there's a whole lot of math here. Let me just go ahead and
pull out a calculator.
Pull out a calculator. So this right here is going to be 0.7 squared. So if I pull out my calculator, squared, so that's 0.49. So what I get here is 0.49 multiplied by negative 60. And if I make a mistake, you'll still get the idea, so don't criticize me. So what we have here is 2 multiplied by 0.7. So 2 multiplied by 0.7 times 0.3, right?
Mm-hmm.
So that gives us 0.42. 0.42 multiplied by negative 9.5 and 72.
Mm-hmm.
Added to 0.3 squared, and that's just 0.9. So 0.9 times 27, comma, negative 2.
Okay.
Do you want me to go ahead and solve the rest of this?
Sure, let's do it.
Okay, so let me go ahead.
Come on, aren't you having a great time?
I'm having a great time.
Awesome.
Let me go ahead and erase this top part.
That's fine.
Let me just erase this top part here. Everyone already knows how everything works.
They can hit rewind, Joel.
They can. So what we're going to do is propagate this across the point. So what we're going to do is 0.49 times negative 60. Let me just kind of clear that up. And then comma 22 times 0.49.
Mm-hmm.
So what we need is 0.49 times negative 60. Mm-hmm. And that's negative 29.4. So negative 29.4, comma, and then 22 multiplied by 0.49, 10.78. And then we're going to add that. So as you can see, there's a lot of calculations going on here, but if you write an application to do this, it's really very, very simple.
Oh, for sure. So
this one's approximately negative 4. And we have 72 times 0.42. So 30.24. I'm rounding just a little bit here to make it easier for me. And for the last one, we have 0.9 multiplied by 27, 24.3. And then finally we have negative 2 multiplied by 0.9, and that's negative 1.8. So finally, once we have all these points, we simply add them together. Okay. So that's negative 29.4 plus negative 4 plus 24.3. So negative 29.4 plus negative 4 plus 24.3, and that's going to give us negative 9.1. So the final answer is going to be negative 9.1, comma, and then 10.78 plus 30.24 plus negative 1.8. So that gives us 39.22. So the final answer is negative 9.1, comma, 39.22. Okay. And unfortunately, the application can't directly help us verify this answer, but if we switch over into our curve design tool and kind of remember that point real quick here. Let me just put my finger there. You can't see me doing this, but So if you look there, we have, what was my final answer again?
You can always alt-tab.
Negative 9.1. Okay, so I'm a little off here. I probably made a mistake here or there. But the y is I really estimated on the x.
Sure.
So that's probably because I estimated a little bit too much. But the y is really, really close, 39 and 41.
Right.
So you get the idea here. If we went through all of the points here and sampled them individually, we would get the entire curve.
Right.
So if I just recap a little bit more here, all I would need to do, I kind of erased the top part, but just replace t with 0, 0.1, 0.2, 0.3.
Like I said, 0 to 1.
Exactly. And with a constant increment, draw a line between those, and you can draw your own line.
Very cool.
So that's the math. Hope that wasn't too painful for you. So if I switch over back into PowerPoint, just a little bit more here. A NURBS curve. Like I said, a NURBS curve is a lot like a Bezier curve, except in this case it has weighting. So for every single point, a weight can be attached to that particular point. So let's see. So the formula that we have here is very similar to what we saw before. Remember, we have the basis spline, which defines a particular function for each of those points. So we have pretty much the same function, except this one is no longer the Bernstein polynomial, but a separate function. And then it's multiplied by the weight, multiplied by the point, and that entire thing is divided by the n, which is the function that we're using, multiplied by the weight. So it's dividing the entire thing by that. And that's where the non-uniform rational B-splines comes from.
Okay.
Because you have a rational, in other words, something that's getting divided by in this particular function. And I was talking about the rational Bezier splines, which does the exact same thing. Each point has a particular weight applied to it. And if we switch over into the application here, I can go ahead and convert this over to a NURBS curve. Switch this over into a 2-degree curve here. And if I select this point here, we can now change the weight on the bottom here.
Which is going to bias the curve.
That's right.
To it.
And exactly. So I have the weight at 80, and now it's almost a right angle with it. Or I could pull it negatively.
It's just pushing it away now.
Which is pushing it away from it. So just a lot more control when you have weighted points for every single one.
Cool.
So that's pretty much all there is to NURBS curve. And with that, I think that's pretty much everything that I wanted to talk about in the discussion section.
Awesome. Again, the idea is just to introduce you guys to curves.
Right.
And the cool thing is Joel has walked all the way through figuring out one of the points along a curve. And now what we're going to do in the next video is put together a very simple program that's going to create a curve for you.
That's right.
Okay, so with that, that's going to wrap up this video. Thanks a lot.